This video will look at some of the basic rules for integrating some common functions. So we have our f of x, which we have defined as the derivative of some function capital F of x. And therefore the relationship between f and little f is that big F equals the indefinite integral of f of x dx. We also have the definition of a definite integral, where the integral from a to b of f of x dx equals the value of big F evaluated at b minus the value at a. Okay, so let's say we have the function f of x equals x squared. All right, so the process of integrating in practice amounts to finding the function whose derivative is your current function. So if you can do that, then you have the indefinite integral of that function. So in this case, let's think about this. What function would give us x squared as its derivative? Well, we know that d dx of x cubed equals 3x squared. So if we take a 1/3 in front of it here, then d dx of 1/3 x cubed would be 1/3 times 3x squared would just be x squared. So that means that the integral of x squared dx is equal to 1/3 x cubed plus a constant. But again, this is not a math playlist. We are not worried about the constant. It usually doesn't matter. Okay, so that's our indefinite integral. We have found that value there. So how would we do the definite integral then? Let's say we're integrating x squared from 1 to 2. Well, we would say that our indefinite integral is 1/3 x cubed, and then we are evaluating that from 1 to 2. So what we do here is we substitute in the value 2, and then we subtract that from substituting in the value of 1. So we have 1/3 2 cubed minus 1/3 1 cubed. Okay, so we've taken the value of 2, substituted that in, the value of 1, substituted that in, subtracting them both. If I factor out the 1/3, I get 1/3. 2 cubed is 8, minus 1 cubed is 1. This is going to give me 7/3 as a result. So the area under the curve between the function and the x-axis from 1 to 2 for x squared is equal to 7/3. All right, cool. Good to know. That's going to come in very useful in lots of the kinds of calculations that we'll do in physical chemistry. But again, we don't want to do this guesswork for a lot of our functions. We want some rules to give us some ideas about what to do. So we have some rules that we're going to write out on the right here in terms of getting what the integrals of some general kinds of functions are. All right, so let's say we have a constant. So we have integral of a dx, where a is some constant, that's going to equal ax, because the derivative of ax is a. So with indicating there that a is some real number. All right, some polynomial function. So as you might have guessed from our little exercise at the beginning, the integral of x to the n dx is going to equal 1 over n plus 1 x to the n plus 1, where n is some integer. And also that, let's see, n is not equal to minus 1. So this works for all polynomials except for x to the minus 1, which we will cover in a second. All right, integral of e to the x. As you might guess, the derivative of e to the x is e to the x, so the integral of e to the x is conveniently e to the x. What a wonderful world. All right, the inverse function, so that is the integral of 1 over x dx. This is the case that I mentioned that this does not hold for. What is the integral of 1 over x? Well, whose function's derivative is 1 over x? That is the natural log. So the integral of 1 over x is the natural log of x. All right, trigonometric functions, our old friends sine and cosine. Integral of sine x dx, well, minus cosine has a derivative of plus sine, so there is that one. And the integral of cosine, the derivative of sine is cosine, so this integral of cosine is sine. All right, these are the common rules for our standard sets of functions for integrals, and our next video will look at some more advanced rules to help us do a little bit better in general.